myself, Hena Shah, Assistant Professor at LG Institutes of Engineering and Technology. So today we are going to discuss few more topics of sequence and series. So let us begin with its first topic, that is nth term test for divergence. Okay? If a positive term series summation n is equal to 1 to infinity un is convergent, then limit n tends to infinity un will be equal to 0. That is, if a series is convergent, then the limit of nth term will be equal to 0. But the converse of the above theorem is not true. That is, if limit n tends to infinity un is equal to 0, then summation n is equal to 1 to infinity un need not be convergent. That is, whenever the limit of n term is 0, we cannot say that the series is convergent. Okay. So now we will specify the test for divergence. So if limit n tends to infinity un is not equal to 0, so the limit of nth term is not equal to 0, then the series un is divergent. Right? Now let us solve an example. Here we have to show that the series summation n is equal to 1 to infinity n square upon phi n square plus 4 diverges. So let us start with the solution. So here you are given un as n square upon phi n square plus 4. Now let us find the limit of un. So limit n tends to infinity un. Put the value of un. Now you have to take out n square common from the denominator. So you will get 5 plus 4 upon n square. Now this n square gets cancelled out. So what will remain? 1 upon 5 plus 4 n square. Now we know limit n tends to infinity 1 upon n is equal to 0. So this term will go to 0. So finally what will remain? 1 upon 5, which is not equal to 0. So what we can say, that the series is divergent by nth term divergence test. Okay. Now let us study one more example. Here is the series 1 plus 4 plus 7 plus 10 plus and so on convergent. We have to check whether it is convergent or not. So let us start the solution. So firstly we will simplify this and find our un. By our formula, Tn is equal to A plus n minus 1 into D. Here your first term, that is A, that is 1 plus n minus 1. D means the difference. So 4 minus 1 will give you 3. Now simplify this. So you will get 1 plus 3n minus 3. So finally you will get your un as 3n minus 2. Now again we will find the limit of un as n tends to infinity. So put the value of un, that is 3n minus 2. Now as n tends to infinity, the whole term will go to infinity, which is not equal to 0. Hence we can say that the given series is divergent by nth term divergence test. Okay. Next, let us study one more test, that is Cauchy's integral test. So if f is a continuous positive decreasing function on closed one open interval infinity and un is equal to f of n. So you will be having functions, right? Then the series summation n is equal to 1 to infinity un converges or diverges if the improper integral integration 1 to infinity f of x dx is finite or infinite. That is, if integration 1 to infinity f of x dx is finite, then we can say that our given series is convergent. And if integration 1 to infinity f of x dx is infinite, then we can say that our given series is divergent. So in this type of examples, whenever we have functions such as tan inverse, sine inverse, etc., what we will do is, firstly we will find integration 1 to infinity f of x dx. If the integral is finite, then our series is convergent, and if it is infinite, then the series is divergent, right? So let us solve few examples. First example is we have to check whether the series summation n is equal to 1 to infinity 1 upon n square plus 1 converges or diverges. Okay, so let us start with the solution. Now replace n by x. So what you will get 1 upon x square plus 1. So this is a function which is continuous, positive, decreasing on closed 1 to open interval infinity. So we can use our integral test. So let us find integration 1 to infinity f of x dx. Put the value of f of x, which is 1 upon x square plus 1. Now this is an improper integral. So wherever you see infinity, you have to write in this manner, that is limit b tends to infinity integration 1 to b 1 upon x square plus 1 dx. Now we know integration of x square plus 1 dx will be equal to what? Tan inverse x. So using this formula we will simplify. So this is equal to limit b tends to infinity. Integration of this will be tan inverse x. Put the limits 1 to b. Now we will put the upper limit and lower limit. So we will get limit b tends to infinity tan inverse b minus tan inverse 1. Okay. Now let us put the limit. So we will get tan inverse infinity minus tan inverse 1. But we know tan inverse infinity is pi by 2 and tan inverse 1 is pi by 4. Simplify this. So you will get answer as pi by 4, which is a finite number. So we can say that series is convergent by integral test. Okay. Let us see one more example. We have to test the convergence of the series summation n is equal to 2 to infinity 1 upon n log n. So again write your un, which is 1 upon n log n, and then can be written as f of n. Therefore our f of x is equal to 1 upon x log x. We have replaced n by what? X, right? Therefore our f of x is a continuous positive decreasing function on closed 2 to open infinity. Now why our interval is starting from 2? Suppose if we put 1, then here it will become 1 upon log 1. But we know the value of log 1. It will be equal to 0. So this will be undefined at n is equal to 1. So our interval is starting from 2. So now we can apply our integral test. So integration 2 to infinity f of x dx. Put the value of f of x, which is 1 upon x log x. Now we will rearrange the terms as we will take this in the numerator. So 1 upon x upon log x dx. And again this is an improper integral. So we have written in the form of limit. Limit m tends to infinity 2 to m. Now we all know the formula of integration f dash of x upon f of x dx. That will be equal to log f of x. So here also the derivative of log, that is 1 upon x, is in the numerator. So we can write this as log x, and limits are 2 to m. So now let us put the limits. So on putting the limits, you will get limit m tends to infinity log m minus log 2. Now as m tends to infinity, the whole term will go to infinity. Therefore we can say that the series is divergent by Cauchy's integral test. Okay. Let us solve one more example. Here we have to test the convergence of the series summation n is equal to 1 to infinity 2 tan inverse n upon 1 plus n square. So here you are given un as 2 tan inverse n upon 1 plus n square, which can be written as f of n. Now replace n by x. So you will get f of x is equal to 2 tan inverse x upon 1 plus x square, which is a continuous positive function decreasing on closed 1 to open infinity, right? So again we can apply our integral test. So let us find integration 1 to infinity f of x dx. Okay. Now put the value of f of x, which is 2 tan inverse x upon 1 plus x square dx. Because this is an improper integral, we will write it in the form of limit. So limit m tends to infinity integration 1 to m to tan inverse x upon 1 plus x square dx. Now we'll assume tan inverse x as t, right? So now dx upon 1 plus x square will be equal to dt. Now let us change the limits. So when x is equal to 1, t will be equal to tan inverse 1. But tan inverse 1 is equal to pi by 4. And when x is equal to m, t will be equals to tan inverse m. Now let us substitute all the values. So we will get integration 1 to infinity f of x dx will be equals to limit m tends to infinity pi by 4 to tan inverse m to t dt. Now just integrate. So answer of this will be t square. Put the limits pi by 4 to tan inverse m, right? So on putting the limits you will get tan inverse m whole square minus pi square by 16. Now if you put m tends to infinity, we will get tan inverse infinity whole square minus pi square by 16. Now we know the value of tan inverse infinity, that is equal to what? Pi by 2. So here it will become pi square by 4 minus pi square by 16. Now simplify. So you will get answer as 3 pi square upon 16, which is a finite answer, right? So we can say that the series is convergent by integral test. Okay. Now let us see one more example. Here we are given the limit n tends to infinity 1 upon n is equal to 0. But we have to prove that our series 1 upon n is divergent. That is, we are given that the limit of nth term is 0, but the series is divergent, right? So let us prove it. So here we are given un as 1 upon n. So which can be written as f of n. Now replace n by x, so you will get f of x is equal to 1 upon x, which is a continuous positive function decreasing on closed one to open infinity, right? So again we will find integration 1 to infinity f of x dx. So this will be equal to integration 1 to infinity 1 upon x dx. Now again this is an improper integral, so we will write in the form of limit m tends to infinity integration 1 to m 1 upon x dx, right? Now integration of 1 upon x will be equal to what? ln x. Put the limits. Now on putting limits you will get limit m tends to infinity ln m minus ln 1. Now as m tends to infinity, the whole term will go to what? Infinity. So what we can say that the given series is divergent by Cauchy's integral test. So here what we have proved? The limit of nth term is 0, but the given series is divergent. So here we have derived that the converse of nth term divergence test is not true. Okay, so we have proved this also. So in today's lecture we have studied nth term divergence test. Nth term divergence test. So if limit n tends to infinity un is not equal to 0, then we can say that our given positive term series is what? Divergent, right? And next we have studied integral test, very important test. So if we are given sigma un, which is a positive term series, right? Where our un is equal to f of n, which is a positive decreasing continuous function, right? Then we have to find integration 1 to infinity f of x dx. If this has finite answer, then we can say that our given series is convergent. And if this has infinite answer, then our given series is divergent. So I hope you have understood throughout the session. Thank you for watching.